Hello guys, welcome back to my channel where we discuss about material science and metallurgy. So let us quickly go to the topic where we have stopped in the previous class, and this is about a very important topic which is called as iron carbide phase diagram. And if you see at the iron carbide phase diagram, which is shown here, it is divided into three portions. This upper part, which is peritectic, and then this zone which is eutectic, and this lower portion which is eutectoid. And you also have three reactions, easy to remember. Then we also focused on the steel part, and then we have tried to understand and analyze what happens at different carbon percentages, how it transforms from the austenite to room temperature. So finally, we are going to get, if it is in the hypo case, we are going to get protectoid ferrite plus perlite. Exactly at point 0.8, only one reaction, that is 100% perlite. If it is more in the hyperutectoid steel, then we are going to get protectoid cementite plus perlite. So these were the things that we have discussed in the previous class. If you have not watched my previous video, please do go and watch that video and then come back. So what we are going to discuss today in this video is about basically, is iron carbide phase diagram a true equilibrium diagram? Then why cementite Fe₃C has 6.67% of carbon to form a compound? Like I promised, we will be discussing that in this session. Then carbon solubility of iron, that is gamma iron, is more than BCC through though the packing factor of BCC is less than FCC. So what is this all about? And we'll try to understand ferrite and cementite present at different carbon percentages. And then we're going to see some important engineering metals which have come from steel. In the next video, we are going to discuss about triple T and CCT. Okay, quickly recall. So what is a liver rule? So in the liver rule, if you see at a given two-phase region, like let us say if this is a two-phase region, what is the amount of liquid and this solid beta to be identified? In such case, the lever rule exists, and the rule says that draw a horizontal line for a given temperature, which is called as tie line. It will intersect at liquidus and solidus part and drop onto the base to read their respective compositions directly. That means this mark here gives us liquid composition and this one will give us solid composition. The second statement says that draw the vertical line at a given composition. So this is the vertical line. It will divide the tie line into two parts. So this is one part and here it is one part. The lengths of these lines are inversely proportional to the amount of faces present. So let me show the same thing with a separate line diagram. So let's say this is M, this part, and here it is N, and this is O. So this side it is solidus and here it is liquidus. And you can see here the reading, that percentage of B is given as 10 and the given data is at 60 and liquidus you have 80. So like I said, lengths are inversely proportional. So if I want this length, that is liquidus, I need to take this length, which is 60 minus 10, 50, and then divide by total length into 100. And if I want solid years, I need to take this length, which is from 80 minus 60, which is 20. So simple sense, if percentage of liquid is given as MO minus NO by MO into 100, and we'll get 50 by 70 into 100 is 71.43, and solid is 20 by 70 into 100, 28.57. If you do 100 minus liquid also, you'll get the same thing. Anyway, why this is important? Because we are going to discuss them in further sessions. So I have just revised it for the benefit of the students. Anyway, moving on, is iron carbide diagram a true equilibrium diagram? The answer is no. The reason being, this iron carbide, which is Fe₃C, is a metastable compound. So when what is metastable? That means it is stable for the time being, but when it is allowed for a prolonged durations of time, it transforms into graphite. So this iron carbide is not stable, it is metastable. So it transforms into graphite for extended period of time, and this is that graphite formation in the iron carbide. This is the actual iron carbide phase diagram. That's why the previous discussions, whatever we have seen, that those diagrams are called not an equilibrium diagram. Okay. Now moving on, why this Fe₃C is having 6.67% of carbon? So Fe₃C, if you break it down, it has one atom of carbon for every three atoms of iron, where the atomic mass of carbon is 12 grams per mole and iron is 56 grams per mole. So when you calculate the percentage of carbon present, 12 by 12 plus 3 times of 56 into 100 will give us 6.67%. That is the reason why. So I hope this is also clarified. Then, all right. So let us understand about the very important justification that asked very often. That is why the carbon solubility of in FCC gamma iron is more than the BCC alpha iron, though the packing factor of BCC is less than FCC. So in order to understand this, so for us, first let us understand the question. So if you remember, we have discussed about the atomic packing factor of BCC. In this case, it is ferrite, which is having 0.68. BCC is having 0.68, nothing but 68 percentage, and it is having 68 percentage of volume occupied by atoms. That means 32 percentage is available free space. Whereas on the FCC, which is face center cubic structure, in this case it is austenite, as 74 percentage is occupied by the interstitial atoms. So what happens here, if you see the maximum carbon, so if you see the iron carbide diagram, the maximum percentage of carbon present in ferrite is only 0.025. Whereas in austenite, it is 2% of carbon. So why this difference? So the answer lies here. If you take the perfect crystal lattice structure, you have let's say BCC crystal structure. And in that BCC crystal structure, the maximum atom that it can fit interstitial space, that is different. So in case of BCC, the maximum or the largest interstitial sphere that it can fit in BCC is 0.36, whereas in FCC, it is 0.52. What does it mean? Suppose if you take FCC crystal structure, it has got some atom space which is available for fitting, and that atom space it can fit is 0.52. So you can see here it is FCC face centered, and you have a larger diameter which is 0.52, and the carbon which is going to go and sit in this interstitial space has got 0.66. Whereas on body centered, you have 0.32. Now, the basic, see, if you take whether it is FCC or BCC, you have less amount available or lesser diameter that it can fit, no doubt. But the distortion which happens, let's say the distortion when it is happening in case of FCC is in a 0.52, you are fitting 0.66. So the distortion is little small compared to the distortion where in case of BCC 0.36 is available, you are fitting 0.66. So that way the distortion will be more. So the crystal lattice distortion, if it is more, what is the problem? The next immediate atom that it can fit interstitially will be very far off. So that is the difference. So in case of uh, body centered BCC, you have more distortion. So the absorption or the carbon solubility is little less than. That is the reason why you have only 0.025% of carbon maximum it can dissolve in the ferrite BCC crystal structure. If you see the face-centered FCC crystal structure, you have 0.52 and you are fitting 0.66. So the distortion is there, but the distortion is comparatively less. So you have more carbon that can be dissolved. So the carbon in FCC is 2%. That is, austenite has got 2% of carbon maximum dissolved. So that is the reason. Moving on. So, what is the amount of ferrite and cementite present at different carbon percentage? So, like in the previous discussion, we were trying to understand if it is in a two-phase region, use a lever rule in order to calculate different two-phase region composition. So, this is a very important case wherein you take different compositions, like for example 0.4, and then try to understand how much percentage of ferrite and cementite or protectide ferrite and perlite that is present, and similarly at various zones you can calculate. So let us quickly see. So in order to get ferrite, you have 0.025, and the given is at 0.4, and the perlite you are getting at 0.8. And let us calculate the values quickly. And you will have protectoid ferrite as 51.61 and perlite as 48.39. And exactly at 0.8. So if you take exactly at 0.8, you have one end ferrite and the other end you have cementite. Cementite is at 6.67. So that if you calculate, you have ferrite percentage as 88.34, cementite is 11.66. Then you can take one at 2% of carbon, and for that you have one side perlite and the other side is cementite. So perlite percentage is 96.59 and protected cementite is 3.41. Okay. Now we'll try to correlate everything and try to understand why is that so important. So at 0.4, if you see, you have protected ferrite and perlite, and 1% you have perlite 96.59 per cementite, then perlite to 2% of carbon, and then protectite cementite. So if you round it off at 0.4, which is somewhere, if you take this as round it off to 0, 0.4, 0.8, it becomes like something like 50. And even this one will be 50-50. So this is how you can, roughly estimate. So at 0.4, you have protectoid ferrite as 50 percentage and perlite as 50 percentage. Suppose if I ask, what about 0.2 percentage? That is somewhere here. That means 75 percentage will be protectoid ferrite and the 25 percentage will be perlite. Let's say 0.6. So that is here. That means 25 percentage will be protectoid ferrite and 75 percentage will be perlite. And what about perlite? At 0.8, it will be 100% perlite. Similarly, if you see 2 percentage maximum, you'll have 79 or 80 percentage perlite and 20 percentage as protectoid cementite. Now, why is this so important? So, if you see ferrite, which is a soft material, very soft and ductile because of less percentage of carbon, and perlite is medium hard because you have a laminar structure of alternate ferrite cementite mixture, so it is perlite. And then finally, this cementite is very hard. That is iron carbide. So whenever you have more and more percentage of cementite coming into picture, you will have more and more hardness and brittleness adding into. So we can vary as per the requirement different carbon percentages, and that is the reason why steel is such an important material, wherein you have very soft and as well as very hard. So you can vary the composition as per the requirement, as per the application needs, and that's why this material has into so many different fields, and this is able to fine tune. The engineers are able to fine tune the composition and select them according to the requirement. So that's all from my side. I hope you like the video. Please do subscribe and share it with those who are interested to know more about the materials and metallurgy subject. Thank you for watching. See you next time.